Hello everyone, welcome back to the GATE lecture series in Engineering Thermodynamics. In today's lecture, we will try to understand the thermodynamic aspects of Otto cycle. Thermodynamic aspects in the sense, the thermodynamic calculations which are related to Otto cycle, like calculating the thermal efficiency, the net work output in the cycle, the mean effective pressure, etc. Right? So now let's quickly see the PV and the TS diagram of Otto cycle. So here it is. This is the PV diagram and this is the Otto cycle on temperature entropy diagram. So now let's consider the PV diagram and try to name all the processes which are involved in Otto cycle. Okay, the process 0 to 1 is called the suction stroke, and the process 1 to 3 is isentropic compression process, 2 to 3 is constant volume heat addition process, 3 to 4 is isentropic expansion process, 4 to 1 is constant volume heat rejection process, and 1 to 0 is the exhaust stroke. Okay, so here there is a note. Generally in the thermodynamic calculations or the thermodynamic analysis, we do not take into consideration the suction stroke and the exhaust stroke. Okay, so we neglect the implications of suction stroke and the exhaust stroke in our thermodynamic calculations. Okay, so eliminating them, the remaining 4 processes, the next thing we need to do is to write the pressure volume or the temperature volume or the pressure temperature relation for each process. So now let's see that in the next slide. The PV, TV and the TP relations in the cycle. So let's quickly draw the Otto cycle. Here we have removed the suction stroke and the exhaust stroke. Okay, we need to define 2 terms here. One is the compression ratio, which is nothing but V1 by V2 or V4 by V3. Okay, so this ratio of V1 by V2 or V4 by V3 is called the compression ratio and it is denoted by R. Okay, so the next one is the pressure ratio, which is nothing but P3 by P2 or P4 by P1. This ratio is called the pressure ratio and it is denoted by RP. Okay, so we will be using both these ratios in our thermodynamic relations of pressure, volume and temperature. So now let's see these relations one by one. Okay, the process 1 to 2 is an isentropic compression process where the relation between P and V is given as P1 V1 power gamma is P2 V2 power gamma. Therefore, P2 is P1 times V1 by V2 whole power gamma. V1 by V2 here is nothing but the compression ratio R. So P2 is equal to P1 times R power gamma. Next, T2 V2 power gamma minus 1 is T1 V1 power gamma minus 1. This is the temperature volume relation. So T2 by T1 is nothing but V1 by V2 whole power gamma minus 1. V1 by V2 again is nothing but the compression ratio. This is equal to R power gamma minus 1. Therefore, T2 is T1 times R power gamma minus 1. This is all in the process 1 to 2. Now let's go to the next process 2 to 3, which is constant volume heat addition process. Here V2 is equal to V3, if you can see it from the PV diagram. So P3 by T3 is nothing but P2 by T2. Therefore, T3 is T2 times P3 by P2. So P3 by P2 is nothing but the pressure ratio RP, which is nothing but T2 times RP. Okay, we already know that T2 is T1 times R power gamma minus 1. So let's substitute that here. We get T3 as T1 times R power gamma minus 1 into RP. Okay, so now let's go to the next process 3 to 4, which is an isentropic expansion process. Here P3 V3 power gamma is P4 V4 power gamma. P3 by P4 is V4 by V3 whole power gamma. Again V4 by V3 is nothing but the compression ratio R. Okay, so P3 is P4 times R power gamma. Right? The next temperature volume relation T3 V3 power gamma minus 1 is T4 V4 power gamma minus 1. So T3 is T4 times V4 by V3 whole power gamma minus 1. Again V4 by V3 is compression ratio R, which is nothing but T4 times R power gamma minus 1. Okay. So in the last process 4 to 1, which is constant volume heat rejection process, we have V4 is equal to V1. You can see it from the PV diagram. Okay. So P4 by P1 is T4 by T1. Again, P4 by P1 is nothing but the pressure ratio Rp. Therefore, T4 by T1 is nothing but Rp. T4 is T1 times Rp. Okay. Here we have expressed T2, T3 and T4 in terms of T1, which is the temperature at the beginning of the compression process, as these relations will be handy in further calculations. Okay. Now we have seen the pressure volume, temperature pressure relations in all the processes involved in this cycle. Okay. Now, once we are clear with the pressure volume and temperature relations for various processes in the cycle, the next step is to understand the heat and the work interactions in the cycle by writing down their expressions with proper sign convention. So let's see that. Let's go to the next slide. Let's draw the PV diagram. Here, if you see in the process 2 to 3, we have heat is supplied to the system. Okay, QS. In the process 4 to 1, heat is rejected from the system. Okay. And in the process 1 to 2, this is a compression process, work is done on the system. Okay. In the process 3 to 4, this is an expansion process, work is done by the system. Okay. We know when work is done on the system, according to the sign convention, it's taken as negative. When work is done by the system, according to the sign convention, it is taken as positive. On the other side, when heat is supplied to the system, we take it as positive. When heat is rejected from the system, we take it as negative. This is a standard sign convention for heat and work interactions. Now, let's see the heat interactions in the cycle in the process 2 to 3. Q2 to 3 is nothing but Q supplied, which is equal to QS. Okay, QS is the notation for Q supplied. This is nothing but MCV times T3 minus T2. Here, should you multiply this with any negative sign? No. Why? Heat is supplied to the system, so it is positive. So no need to multiply with a negative sign. You can take the expression as it is. Now let's go to the process 4 to 1. Here Q4 to 1 is Q rejected, and Q rejected in notation form we write it as QR, which is nothing but MCV times T1 minus T4. Should you apply any sign convention here? Yes, we need to apply the sign convention because heat is rejected from the system, and you need to multiply this expression with a negative sign, which gives minus MCV times T1 minus T4, which is MCV times T4 minus T1. So this is Q rejected. This is not Q rejected. Okay, you have to apply the sign convention when you are writing the heat interactions, when heat is supplied to the system, when heat is rejected to the system. Right? You're clear now with the heat interactions in the cycle. Now let's go to the work interactions in different processes. In process 1 to 2, which is an isentropic compression process, work done in an isentropic process 1 to 2 is nothing but P1 V1 minus P2 V2 by gamma minus 1. Should you apply a sign convention here? Yes, you need to apply a sign convention because work is done on the system. It's a compression process. So according to sign convention, you multiply it with negative sign. So work done in the process 1 to 2 is negative of P1 V1 minus P2 V2 by gamma minus 1, which is nothing but P2 V2 minus P1 V1 by gamma minus 1. So this is the work done in the process 1 to 2. Okay. So the next process is 2 to 3, which is constant volume heat addition. As volume is constant, the work done is 0. This is quite straightforward. Now let's take the next process 3 to 4, isentropic expansion process. So work done in an isentropic process 3 to 4 is P3 V3 minus P4 V4 by gamma minus 1. Should we apply any sign convention here? No, we can take the expression as it is. Why? because work is done by the system. So according to the sign convention, work done in the process 3 to 4 is P3 V3 minus P4 V4 by gamma minus 1. Okay, you take this as it is. What is the last process? 4 to 1, which is constant volume heat rejection process. Here work done is 0 because there is no change in volume. So these are the heat and the work interactions in different processes in the cycle. Okay, so with this basic understanding and knowledge of the pressure, volume, temperature relations in various processes in the cycle and the heat and the work interactions in different processes in the cycle, we will now try to derive the expressions for thermal efficiency, network output and mean effective pressure. So the first one is thermal efficiency. How do you define thermal efficiency? Thermal efficiency of an Otto cycle is defined as the net work done divided by the Q supplied. So from the first law of thermodynamics, the net work done is nothing but Q supplied minus Q rejected by Q supplied. So in the notation form, we write it as Qs minus Qr by Qs. Now considering the constant volume processes 2 to 3 and 4 to 1, we have seen these expressions in the previous slide. Qs is nothing but mCv times T3 minus T2. QR is nothing but mCv times T4 minus T1. These are already taken with sign conventions. Okay, so you need not change anything here again. So now just substitute them in this particular expression. What is that you get? Efficiency of Otto cycle is m times T3 minus T2 minus m times T4 minus T1 by m times T3 minus T2. Okay, the CV is cancelled in the numerator. It is common. You can cancel m also in the numerator and the denominator. Upon simplification, you get it as 1 minus T4 minus T1 by T3 minus T2. Okay, so let's have these relations handy. Okay, to simplify this particular expression, here we take T1 common in the numerator. This will give T4 by T1 minus 1. And let's take T2 common in the denominator. This will give T3 by T2 minus 1. So here you can see T3 by T2 is nothing but T4 by T1. Okay, so you can cancel them and you are left out with the expression 1 minus T1 by T2. So T1 by T2 is V2 by V1 whole power gamma minus 1. So if you take that into denominator, it becomes 1 minus 1 by V1 by V2 whole power gamma minus 1. V1 by V2 is nothing but the compression ratio R. Okay, substitute that, you get efficiency of Otto cycle as 1 minus 1 by R power gamma minus 1. This is the expression for efficiency of Otto cycle. Okay, it is dependent on the compression ratio. Alright, okay. Whether efficiency will increase or decrease, we will see sometime later. Okay, for now, this is the expression. Okay, so what is the next thing that we need to derive? The expression for network output. So the network output for an Otto cycle can be expressed as P3 V3 minus P4 V4 by gamma minus 1. This is work done in an expansion process, work done by the system minus work done on the system. P2 V2 minus P1 V1 by gamma minus 1. Here already we have taken these expressions with proper sign convention. So there is no need to take sign convention again here. So if you simplify this, take P1 V1 by gamma minus 1 common here. Okay. And write the remaining expression, which is nothing but P3 V3 by P1 V1 minus P4 V4 by P1 V1 minus P2 V2 by P1 V1. Minus of minus is plus. P1 V1 by gamma minus 1, you have taken it outside the bracket. Okay, so you will be having plus 1 here. Now let's keep few relations handy. Okay, to simplify this. Here, in simplifying this, we expand the expression in the bracket as P3 by P2 into P2 by P1 into V3 by V1. V3 is nothing but V2. Okay, minus P4 by P1 into V4 by V1 minus P2 by P1 into V2 by V1 plus 1. Okay, V1 and V4 are one and the same, so you can cancel them, right? Here P3 by P2 is nothing but Rp. P2 by P1 is nothing but R power gamma. V2 by V1, okay, V2 by V1 is 1 by R. Okay, P4 by P1, okay, P4 by P1 is Rp. P2 by P1 is R power gamma. V2 by V1 is 1 by R plus 1. Okay, so you have expression in terms of R or Rp for all these terms, okay, which are there in the bracket. So we write it as P1 V1 by gamma minus 1 into P3 by P2 is Rp. P2 by P1 is R power gamma. V2 by V1 is 1 by R. Okay, minus P4 by P1 is Rp minus P2 by P1 is R power gamma. V2 by V1 is 1 by R plus 1. Okay, so this splitting you must remember when you are trying to reduce this particular expression. Okay, so upon further simplification you get P1 V1 by gamma minus 1 into Rp into R power gamma minus 1 minus Rp minus R power gamma minus 1 plus 1. Okay, so you can factorize this further and you can get the final expression as P1 V1 by gamma minus 1 into Rp minus 1 into R power gamma minus 1 minus 1. This is the net work output in an Otto cycle. Okay, so only this step is little critical. You need to split and try to use the relations which you have derived in the second slide, the pressure, volume and the temperature relations for each and every process. Okay, other than that the simplification is quite simple. So the next thing we are going to derive is the expression for mean effective pressure. So the mean effective pressure of a cycle is given by work output by the swept volume. So work output in the previous slide we have the expression as P1 V1 by gamma minus 1 into Rp minus 1 into R power gamma minus 1 minus 1. And what is the swept volume in the cycle? V1 minus V2. You can take V1 common, V1 times 1 minus V2 by V1. V2 by V1 is nothing but 1 by R. Okay, now plug these two expressions in this formula and you get mean effective pressure as P1 V1 into Rp minus 1 into R power gamma minus 1 by gamma minus 1. This is the work output. Okay, by swept volume. Swept volume is V1 into 1 minus 1 by R. V1 into 1 minus 1 by R. So V1 and V1 you can cancel, and 1 minus 1 by R you can write it as R minus 1 by R, and this R in the denominator will go into the numerator here. Okay, which is nothing but P1 times R into Rp minus 1 into R power gamma minus 1 by gamma minus 1 into R minus 1. This is the expression for mean effective pressure. Okay, so we have derived the expression for thermal efficiency of an Otto cycle, the net work output in an Otto cycle, and the mean effective pressure. So these three are very important thermodynamic quantities that we need to know when we are doing thermodynamic analysis of an Otto cycle. Okay, now initially when we were deriving the expression for thermal efficiency, I said we must know what is the effect of this compression ratio R and the specific heat ratio gamma on efficiency of Otto cycle. You will not get pressure ratio in the expression for thermal efficiency. Thermal efficiency is only a function of compression ratio. Okay, so if you see, when you increase the compression ratio, the thermal efficiency of the Otto cycle also increases. Okay, this is because a higher compression ratio will lead to a greater temperature and pressure at the end of the compression stroke. Okay, what will this do? This will result in more energy being extracted from the combustion process during the expansion stroke. You can extract more energy, okay, from the combustion process during the expansion stroke, right? So when there is an increase in the compression ratio, there is an increase in the thermal efficiency of an Otto cycle. Now what about the specific heat ratio? If the specific heat ratio increases, the thermal efficiency of the Otto cycle also increases. Okay, why? This is because a higher gamma leads to a greater difference in temperature during the heat addition and heat rejection processes, allowing for more work to be extracted from the cycle. That is the reason whenever the specific heat ratio increases, there is an increase in thermal efficiency of an Otto cycle. So in short, for compression ratio, higher value of compression ratio, higher efficiency, but there are few practical limits which I'll be discussing when I'll be teaching the diesel cycle. For specific heat ratio, higher gamma, higher efficiency. Okay, so to conclude, both the compression ratio and the specific heat ratio significantly impact the thermal efficiency of the Otto cycle, with higher values leading to increased efficiency up to practical limits for each parameter. These practical limits we will discuss when we are doing diesel cycle. This is all about Otto cycle, the thermal analysis or the thermodynamic analysis of an Otto cycle. Okay, so in short, let us summarize what is that we have seen. The first thing is the PV diagram, the TS diagram, okay, of an Otto cycle. The next one is the pressure, volume, temperature relations in an Otto cycle of various processes in an Otto cycle. And we have introduced terms called compression ratio and pressure ratio in these relations. Then we have seen the heat and the work interactions in various processes in the cycle. We applied the sign convention and we derived the expressions for heat and the work interactions. Then we calculated the expressions for thermal efficiency, work output, and mean effective pressure in an Otto cycle. At last, we have seen the effects of compression ratio and specific heat ratio on efficiency of an Otto cycle, where the increase or the higher values of compression ratio or the specific heat ratio will increase the thermal efficiency of an Otto cycle. Okay, of course, there are few limitations to these parameters which we will be seeing in the diesel cycle. I suppose now you are very clear with the relations involved in Otto cycle, and you will be ready for solving problems related to Otto cycle. I will be back discussing another cycle in my next video. Till then, thanks for watching and do take care.